Good morning. Okay, I hope that you're doing fine. It's the third day of the lecture with the online collaborate. I am going to start with chapter 2, but you will have time to ask some questions later if you have any questions about chapter 1. Any concerns at this point? No? Is everything all right? Can we start? Okay. Do you have the PowerPoint available to you now? I didn't click on share, but I just want to make sure. Okay, perfect. Perfect. Thank you. Thank you. Okay. We're going to talk about the structure and properties of organic molecule in chapter 2. Basically, we are going to see how the bonds are forming in organic chemistry, bonds between carbon and other carbon and other elements of the heteroatoms that we talked. And we're going to emphasize on hybridization of the carbon that is going to determine the structure of the molecule. When we say hybridization, what does it come to your mind? When we talk about hybridization, what does hybridization mean to you? Hybridization, it's mixing of two different species, right? When we talk about hybridization, it could be hybridization between two plants, two animals, here two species. Now, when hybridization takes place, there are some conditions that they should be both very similar enough to each other. So they cannot be like two-way off, like you cannot probably hybrid oranges with what would be impossible these days? Oranges with watermelon. But oranges with tangerine, you can't hybrid. When you do hybridization of oranges and tangerine, you get like a tangelo. If you ever had tangelo, it looks like nothing like orange, nothing like tangerine, but something in between. So the taste is kind of a mixture of the two. In hybridization or formation of a bond, when in molecules between the two atoms, when you bring two atoms close to one another, this is for formation of the bond, because formation of bond happens between two atoms. Which subatomic particles is going to interact or face each other first? They would be electrons, right? Electrons, because your neutrons and protons are inside the nucleus, and when they are inside the nucleus, there is no interaction between the two nucleuses because they are out of touch. That the other name for nucleus was do not touch them. So when you bring the two atoms of two elements together, the first thing that they are going to touch or see is going to be the electrons. And where the electrons are housed, what is the place that electrons are in? That is called orbital, right? When the orbitals are very good. Orbitals they are going to overlap with one another. The orbitals from one element, orbital from one atoms of one element, and then orbital of atom from another element, they can overlap. When they do overlap, there are two types of overlap. Sometimes the overlap is constructive, and another times the overlap is destructive. What does constructive and destructive refer to? It's like we have to give like wave-like property or wave nature to the electron. Then we say electrons are like wave. They have wave-like property. So the orbitals, when they are overlapping, sometimes they could be constructive and other times could be canceling each other's effect. When they are constructive, they are going to enforce each other. Let me show you another picture of the constructive and destructive. And I can come back to this. So when it's constructive, you're going to see this. They are enforcing each other. And when it's destructive, the overlap is going to kind of cancel each other's effect. They are not enforcing each other. So as a result of constructive overlap, you will see a molecular bonding or bonding molecular orbital. And as a result of a destructive, which is this type, destructive, is going to form anti-bonding orbital. So when you have anti-bonding orbital and versus here you have a bonding orbital. Remember when I was talking about the difference between s orbital and p orbital in the same energy level, like energy level 2, s orbital has less energy than p orbital, and that was because of the shape of the orbital, for s being spherical and for p being dumbbell shape. So dumbbell shape orbital has higher energy than spherical. Compare these two, bonding versus anti-bonding. You see how hard it is for electron to be in this anti-bonding orbital. So when you have anti-bonding, there is really no point for electron to go to the anti-bonding, because formation of a bond, when you have two elements forming bond, one of the purposes for the elements, the two atoms to form a bond, to become stable. Like if they are sharing electrons, they are trying to satisfy the octet. And if they want to satisfy the octet, they want to be more stable. And if they are being more stable, they want to have a place. And when we talk about the place for electrons, we're talking about orbital. That could be molecular orbital, that could be atomic orbital. But when the molecular orbital forms, you want to have a shape like a bonding orbital for electron, or electron after formation of the bond is going to go to bonding orbital, not to anti-bonding orbital, because anti-bonding orbital is going to have very high energy. So I'm not teaching entirely like the molecular orbital. I just want to show you the difference between a bonding and anti-bonding orbital. So when you have destructive overlap, when you have constructive overlap, how do they look like? Because later on, when I tell you that bonding or orbital has less energy than atomic orbital, anti-bonding has higher energy than atomic orbital, at least you could picture these two, bonding and anti-bonding sigma orbital. So let's say you have hydrogen atom with one s orbital, and then another hydrogen atom with one s orbital. This is a 1s with one electron, and then this is 1s with another electron. So if these two have constructive overlap, they are going to form bond, they are going to overlap, and form a molecular orbital. So your molecular orbital is going to have, in terms of the energy level, the energy of the molecular orbital, if it's bonding, is going to be less than each individual atomic orbital. Now, if is destructive, is going to be forming another molecular orbital, but that other molecular orbital is going to have higher energy compared to the atomic orbital that you have there. So this is known as the anti-bonding. And you notice that I started with one s orbital from one hydrogen, another s orbital from another hydrogen. I am adding two orbitals together. If I add two orbitals, addition of orbitals, it's linear addition. What does it mean? It means 1 plus 1 is 2. So one s orbital from hydrogen 1, one s orbital from hydrogen 2 is going to give me two molecular orbitals. Only one of the molecular orbitals is the perfect one, is the desired. It has less energy because when two hydrogen forming bond, they would want to look like helium. Each one is going to form like feel like helium, because when you have the sharing of the bonds, that you count the shared electrons toward both nucleuses, and each one is going to have two electrons. That means satisfaction for hydrogen. That means stability for hydrogen. And if it means stability and satisfaction for hydrogen, means the electrons are going to have less energy now. So the electrons are going to go down to a molecular orbital, and they are going to spin with opposite direction. So when you look at this small diagram, simple diagram for molecular orbital of the formation of hydrogen, you have bonding molecular orbital, you have anti-bonding molecular orbital, you have two electrons that you begin with, and those two electrons now they come to reside inside the bonding molecular orbital. This is when the bond forms between the two atoms. But just one other definition I want to mention before we move. If the combination of the orbitals are between different atoms, you will see bond formation. If the combination of the orbitals is coming from the same atom, it's not bonding. Instead, is hybridization. So hybridization is going to happen between the orbitals of the same atom, not two different atoms. So if it's one hydrogen, hydrogen 1 and hydrogen 2, or a carbon and another hydrogen, you will get a formation of a bond. But hybridization is the merging or overlap of orbital or combination or mixing of different orbitals of the same atom. So because we gave the wave nature to the electrons, so when when we are combining the two orbitals, we basically saying they are just combining waves, and waves, they could be constructive, so they enforce each other, or they could be destructive, and when you have destructive, is going to cancel each other's effect. So with the canceling each other's effect, you would get anti-bonding. Okay. And formation of a bond, it results in stability, lower energy level. So the bonding molecular orbital is preferable. Yes, bonding molecular orbital, they are going to have less energy. So your electrons, after they are sharing, so you bring the two orbitals together, you also are going to take care of the electrons that you had in your atomic orbital. You had one electron in atomic orbital 1, you had another electron in atomic orbital 2. When you form this house, the new place, the new orbital, which you call it now molecular orbital rather than the atomic orbital you had before. Now you want to bring the electrons. So if you have 2 electrons, one from each, they are going to come and stay in this molecular bonding orbital. Non-bonding or anti-bonding orbital is going to often stay empty. If the electron is forced to go to anti-bonding, it's going to push the 2 nucleuses away. Basically, it's repelling each other. So they are not going to be stable. Electrons in anti-bondings are not stable because just look at the energy diagram here. It's a better picture. Energy diagram for atomic orbital is right here. And then you have your bonding orbital, which is much lower. Anti-bonding is much higher. Much higher energy level means what? Is less stability. So if electrons are not stable, they are not going to go to the anti-bonding, and they are not going because they are not stable, or it needs a lot more energy. What was the purpose of forming bond to begin with? Let's say if you have 2 hydrogen, they form bond to be more stable. So if they want to be more stable, why would they go to anti-bonding to have much higher energy than even they were before? Okay. So if you have electrons in anti-bonding, it's going to make it unstable. So if you have 2 p orbitals, same thing. So the previous slide was showing 2 s orbital overlap of 2 p orbital. It could be constructive. You get bonding. And please, just one other thing that I had to mention: if you have 2 p orbitals, this overlap is like a head-on, is not side by side. So head-on overlap. So you see this blue part of the orbital p from right side with the blue from the left side is coming together and is forming overlap. There is overlapping and is creating this more stable, a bigger cloud, because you have small cloud, 2 small clouds, and here when they join, it gives you like a bigger cloud, and that bigger cloud is called your molecular orbital. Your molecular orbital, comparing to atomic orbital of the p orbital, is going to have less energy, is going to be more stable. And if it's anti-bonding, that means that they are destructive. Their destructive overlap is going to create anti-bonding much higher energy than original p orbital separately. So is not a desired one. So if you have s and p orbital, with the s and p orbital, see this constructive overlap. You have your positive side from the p orbital and a positive from your, and then your s orbital. So you could go with the shade of the color. If it's constructive, is going to give you a stable or bonding, and if it's destructive, it's kind of diagrammed or shown with different color. So you could see that is destructive, because then you don't have to always draw the waves, how they are going to be destructive, or I'm sorry, my wave was pointy. If it's destructive, is going to give you higher energy orbital as a result. If it's constructive, it would give you lower energy. So is this showing like different color or the same color is a translation of the waves being added, constructive or destructive. So if it's the same color facing each other, it would be constructive. Different color, it would be destructive. If you were given, let's say for the quiz, if you were given two orbital added together with the same shade of blue, then you would say this is going to give bonding. Or if it's like different shade, one green, one blue, then you would say this overlap is going to be anti-bonding. So all is trying to say, all is trying to introduce to you, even though I'm not going to emphasize a lot on the molecular orbital, but I want you to understand later, if we say stability of the molecule, it depends on where the electrons are. If the electrons are in the bonding orbital or anti-bonding orbital, you understand what is happening. The bonding orbital, they have less energy than atomic orbital, and anti-bonding, they have higher energy. So if they are different color represented by different color, that means destructive. Same color overlap is going to be constructive. Okay, another type of overlap is the overlap between two p orbital, but when your p orbitals are facing each other parallel, they are not head-on. If they are facing each other in parallel position, the type of molecular orbital that is going to form is different. And you see this like little space between the blue and the green loops of the p orbital, even in bonding orbital. I'm going to point it to, like, with the red color right here, you have some space, okay? Some space. So it's like if you bring like the two thumbs together, trying to bring the two p orbitals together, there's a space between them. It's like, I often say, well, it looks like that someone, a contractor comes and builds a house for you, but it puts like a big hole in the ground, and then when you are walking, you have to be careful where to go. So electrons are going to be shy how to walk around there, or how to orbit and how to rotate in that space, because not allowed in this empty space. So what is the damage, or what is the disadvantage of that? When you are getting a pi bond is going to be weaker than sigma bond. So this type of molecular orbital is called the pi orbital, is not a sigma orbital. What we had before for a head-on collision right here, this is a sigma bonding. When you have the side-by-side, this is a pi bonding. So when you have your pi bonding orbital, that is the result of it. There's only one type of pi bonding, and that must be two p orbital coming together side by side. And you see, if the blue colors are facing each other, even side by side, you get the molecular orbital that is called bonding. If it's the green and blue facing each other, it would be anti-bonding. This is just diagram that it shows how the anti-bonding is formed, but the main justification is the energy level. Energy level for anti-bonding is much higher than atomic orbitals. Then you have your pi molecular orbital that is forming. Is like a half a pi up and half a pi down here along the nucleus line. Okay, so when bond forms, formation of a bond is between two separate orbitals of two separate atoms. When hybridization forms, hybridization is overlap of orbital for the same atom. So s orbital from carbon, for example, p orbital from carbon is going to form bond and is going to Sorry, I was just reading your question. The is going to have a mixture of the two character of S and P for hybrid orbital, and we will talk and emphasize on that. The question was, so the pi bond has higher energy. Exactly, pi bond has higher energy than the sigma bond. But you probably knew from before that pi bond is weaker than sigma bond, which goes with the same line. Weaker bond meaning you can break it easier. So how do you break a bond? You give energy. Pi bond already has more energy, is less stable, has more energy. So with a little bit of more higher energy, you can break it. Sigma bond has less energy, so if it has lower energy, it's more stable, is a stronger bond. If you want to break that bond, you have to spend more energy. So pi bond in general is less stable and weaker than a sigma bond. Where do you see pi bond? You must have the sigma bond forming first, and if you have double bond, the first one is sigma, the second one is going to be the pi bond. So pi bond is always the second bond that is forming, or any additional bond that is forming. Okay, formation of methane. How does molecule of methane forms based on using the orbital diagram? If we talk about the orbital diagram, that means we are going to have the s orbital. Let's say the way that carbon is, we had the electron configuration for carbon. We had the 1s, 2s, and then you have 2px, 2py, and the 2pz was actually empty. So you have one electron, two electrons, and two electrons. Now, based on the orbital theory, if we go with the orbital theory, you have a hydrogen that has one s orbital. The bonding is going to form only between orbitals that they have single electrons. So the bonding between orbital of 2px with the hydrogen, because 2px has one electron and hydrogen has one electron, so these two is going to be overlapping and forming bond. And another hydrogen with one s, one electron, is going to form the second bond with the 2py. So if we go with the molecular bonding, then this is not going to be justified. How come carbon can form 4 bonds if it has only 2 orbitals with single electrons? The solution, it comes from the hybridization. Hybridization can explain that. Based on the hybridization, so it's going to say first, if we have the 1s with 2 electron and 2s with 2 electron, you have your 2px, 2py, and 2pz, 1 electron, 1 electron. First excitation is going to take place, and 1 electron from 2s orbital is going to go to 2pz. Now you are going to have 1 electron in after the excitation. You are going to have 1 electron in s and 1 electron in every 2p orbital. So now it's going to make it easier for 4 hydrogen to form bond with carbon. So this was a justification how 4 bond can form, how carbon can form 4 bonds. The shape of the p orbital is different from shape of the s orbital. So if I use the same space again, so you have your notes. So I'm going to draw the possible formation of the bond if carbon atom starts forming bond the way that it shows here. Good question. Can the electron go from 2s, or can it go from 1s? Good question. And I'm going to go back to example that I had, orange and tangerine forming bond, but not orange with watermelon, forming hybrid plant or fruit. So in order for excitation and hybridization, one of the conditions is that your hybrid, your atomic orbital, they must be close enough in energy. So it's worth it, it's beneficial for us to move one electron from 1s to go to 2pz. It takes less energy, but to go from 1s to 2pz instead of 2s to 2pz, this is going to take a lot more energy and is not going to be beneficial. So it's better to go from 2s, and that's what's happening, is going from 2s, not 1s. Good question. But it's going back to what I said earlier. They have to have close enough energy, and one of the orbitals is going to be, it requires less energy. Very good, Amanda. Yes, exactly. So you're welcome. So if we take this possibility for carbon and say that this is going to form the 4 bonds with the 4 different hydrogens, what is going to happen? You have s orbital. You have s orbital from carbon. This is the carbon s orbital. And then you have s orbital from hydrogen. That is going to overlap. You have p orbital from carbon, that forming bond with s orbital for hydrogen 2. So I'm going to put hydrogen 1, hydrogen 2. This is the p orbital from carbon, p of the carbon. So another p orbital from carbon and s orbital from hydrogen, and the third p orbital from carbon and s orbital from hydrogen. So this is the hydrogen, that's carbon, hydrogen, hydrogen and carbon. Sorry, this is the carbon. So we have the p orbital with s orbital, we have 2 s orbitals, and then we have another p orbital with the hydrogen. So there is 1 bond here, 1 bond, 1 bond. 3 bonds is coming from s and p overlap, and 1 bond is coming from s orbital. I hope you get it. We have different nature of the orbital overlapping now. If the bond is between s and s, because they are 2 small bonds, and the type of molecular orbit or the bond that is going to form is going to be more condensed, is going to be short bond compared to this bond of the p orbital with the s orbital. Now, if this is true, if that is true, when carbon forms bond with 4 hydrogens, you are going to have 1 short bond and 3 long bonds. So this is if one of the orbital from carbon is s and the other 3 are p orbitals, when they form the bond, you are going to end up with 1 short bond and 3 long bonds. But when they take X-ray of methane, they find out that methane has 4 bonds, and those 4 bonds are exactly identical, same length. So this is denied. says you cannot have one s orbital for carbon and 3 p orbitals for carbon. So what is the solution? The solution was formation of hybrid orbitals. So I'm going to use the same space here to show how hybrid orbital is going to form. And what makes the what made the people to look for a solution that now we have a hybrid orbital, or we have the concept of hybridization, was this difference in the length. If we had unhybrid orbital, just the one s orbital from carbon with one electron from the 2s of the carbon and one electron from the 2px, 2pz, and 2py of the carbon, then we would have ended up with this structure. But when they take the X-ray, X-ray can see the nucleus of the atoms and can measure the bond length. They found out that this is true, not this one. What is this is the 4 identical bond length for the carbon and hydrogens. So they justified it based on hybridization. What is hybridization? Hybridization means that electrons that they are in different energy level, now they are going to mix the orbitals. When you mix the orbitals, they are going to form new orbitals. So basically overlapping of atomic orbital from the carbon is going to form new orbitals. The new orbital is going to have new name for it. So the example that I usually use is like you have a yellow color Play-Doh and you have blue color Play-Doh that you mix it together. Let's say you have 1 box of yellow color Play-Doh and then you have 3 boxes of blue color Play-Doh. You put them all together, you mix it very well, and you put it back in the boxes again. How many boxes of Play-Doh would you get? Would you end up with? Okay, 1 box of yellow color, 3 boxes of, very good. 1 box of yellow color, 3 boxes of blue color. It's Play-Doh. When you mix it together, you are going to end up with 4 boxes. Like 1 cup of one with 3 cups of other is going to give you 4 cups. And we talked about this earlier and said addition of orbital is linear. That means 1 plus 3 is going to be 4. This is your s orbital combining with 3p orbital, and it is going to give you 4 new orbital. And that's like the new orbital. What color would be your Play-Doh? Green color? It's okay. What color would be the Play-Doh? Play-Doh is going to be green color. Very good. So you would have a green color Play-Doh, and it's something in between. So it's not the yellow color, it's not the blue color, it's the green color. So since the color is new, now when you are mixing orbital, the new orbital that is forming, you have to name it new. You cannot say s orbital, you cannot say p orbital. So they chose a new name for this hybrid orbital, and they named this hybrid orbital sp3 orbital. So sp3 orbital is not 4 orbitals. sp3 orbital is just one sp3 orbital. But what does it mean? It means that this orbital is 1/4 s, and 3/4 is going to be p, or it's coming from hybridization of 1 s orbital with 3 p orbital. So when you mix the they use this, has more space. So when you mix the 2s with 1 electron and the 3p orbitals, each one with 1 electron, After you mix them, basically blend it together, just like mixing the yellow color and blue color together, you are going to end up with four hybrid orbital. And your hybrid orbital is not going to be at the energy level of P, is not going to be at the energy level of S, it's going to be somewhere in between. So it's going to be 1, 2, 3, 4. And each one of these is called sp3. And that sp3 was the solution to naming. Says, okay, we're just going to say sp3 because it's coming from one s orbital and 3 p orbitals. But the total is going to be 4 orbitals. Now you have 1 electron in each. For carbon atom, after excitation, you end up with 1 electron in each. And then after hybridization, you end up with 4 orbitals with the same energy level. 4 orbitals with the same energy level. Now it's ready to form the bond between 4 hydrogens, because now if you bring the s hydrogen, the s orbital from the hydrogen, you have s orbital from hydrogen, 4 different hydrogens. Now when you form bond, these bonds are going to be identical, and if they are identical, they are going to show same bond length, and the new or the structure that was shown from the X-ray or the 3D structure, it's justified and it does make sense. One thing that we want to talk about here is the shape of this orbitals, how they, with respect to each other, how would they they are oriented in the space. When you have sp3 hybrid, for sp3 hybrid that your carbon atom has, is going to have tetrahedral. Tetrahedral, it looks like this shape. Okay, tetrahedral shape. And then your s orbital is going to come and form bond with this hybrid orbitals, and after the bond forms, is going to be, your molecule is going to be also tetrahedral. But why tetrahedral? Because you have 4 orbitals that they are attached to this carbon. Orbitals, each one they have 1 electron. And if you take like 2 balloons, fill it up with air, same size balloon, and fill it up with air, and you knot the end of the 2 balloons together, what would be the most stable? What would be the best way that they are going to stay or align with respect to each other? If you have only 2 balloons and you knot the ends together, would they go like this with respect to each other, or they would be straight? Linear, very good. It's going to be linear. So if you have 2 balloons, it's going to be linear. So if I take these 2 pens, I don't know if the video is clear or not. I'm going to say that this is the video clear? You could see me? Okay. I'm going to say these 2 are 2 orbitals, or the 2 balloons, and the heads with the black heads, they don't like each other because they have negative charge. And if they have negative charge, they are going to go, they are going to go as far as possible from each other, and it's going to be linear. What happens if you have 3 of them? Maximum space from each other is going to look like this. Do you see that? It looks like a triangle. It's planar, right? It looks like triangle is planar, so it's called trigonal planar or trigonal planar. So it still is in the one plane, and it looks like a triangle. So you have this when you have 3 hybrid orbital. When you have only 2 hybrid orbital, it's going to be linear. When you have 3 hybrid orbital, it's going to be trigonal planar, like this. Now, what happens if you have 4? So let me just go back to that, please, because it's going to save some time later. If you have 2 hybrid orbital, the bond angle is going to be 180. You have bond angle being 180. If you have 3 O hybrid orbital in one plane, maximum distance is going to be 120 bond angle. So is a trigonal planar with the 120 bond angle. Now, if we have 4 hybrid orbitals, that is the case for sp3 of the carbon. If we have 4 hybrid orbitals, they are trying to get in line, and each is going to form for a perpendicular to one another, looks like it, and this angle is going to be 90 degrees. These are not feeling comfortable. It's like the back seat of your car has 3 seat belts and you force 4 people in there, and how would you make each other comfortable? If all 4 of you lean against the seat and sit back, it's going to make everybody uncomfortable. So often, I don't know, and I hope you don't do that often, but I don't know if you have the experience. One of the people, if leans forward, then the other 3 is going to be more comfortable, at least, manageable for the destination. So what's going to happen for this? One bond is going to go up, one hybrid orbital is going to go up, and 3 would go down. And that gives a shape of tetrahedral. And what this shape of tetrahedral is going to do is going to increase the bond angle. Increasing bond angle, what does it mean, increasing bond angle? How does it benefit? It's going to give more space between the orbitals, and more space between the orbitals, that means more distance between the negative charges, that means more stability. So when you have 4 hybrid orbital, you're not going to get the 90-degree angle. You will get the 109.5 if all of them are same element. Is going to be, if they are all bonding, is going to be 109.5 degree angle for the hybridization, for the tetrahedral shape sp3 hybrid orbital. Any questions about the sp3 hybrid, how is formed, and how do we justify the bond angle? Here is going to be 109, 109.5 bond angle, and the shape is going to be tetrahedral. Now, I'm going to take you a step back and I tell you where did we start and what we end up with. We started with 1s2, 2s2, and 2p2, and we were confused and surprised how come the bond, the compound that is formed between a hydrogen and carbon is not CH2 and is CH4. How does carbon can form 4 bonds? Because it has only 2 p orbitals with 1 single electron each. So is expected to form only 2 bonds, but this never exists. The CH2 does not exist. Instead, we have a CH4. So in order for carbon to form 4 bonds, it must have 4 single electrons. So we excite 1 electron from s orbital and take it to the p orbital, the 3rd p orbital that is empty. Now we have 4 single electrons. That would justify the 4 bonds, but it still does not justify the shape and the bond angle. Why it doesn't justify the shape? Because the x, y, and z axis are parallel, perpendicular to each other. So if we had the px, py, pz forming bond with s orbital, the bond angle must have been 90 degrees. So px, py, pz, they are named because they are actually parallel to the x, y, z axis. So if we had the bond between the p orbitals before hybridization, the bond angle should have been 90 degrees. But When they measure the bond using the X-ray, they find that it's not 90 degrees and it is 109. So hybridization basically solved two problems. One, number of orbitals with the single electrons that is ready to form bond, and two, the shape of the orbital, because the shape of orbital, the shape of the molecule that is tetrahedral, and the bond angle was justified to be of 109. Questions? Okay. So hybrid orbital is coming from mixing of the two atomic orbital. The process of mixing atomic orbital to approach each other to form the bond is called hybridization. Basically mixing in terms of the energy level. So you kind of bring to the same energy level. S orbital has less energy, p orbital has more energy. When you mix them together, they all have same energy level. Okay, this is a better drawing of tetrahedra with the 109 bond angle, carbon forming bond with 4 hydrogen, all symmetrical. Now, how would you justify formation of carbon-carbon double bond? What is carbon-carbon double bond, or under what condition carbon-carbon double bond forms, and carbon-carbon triple bond? So these are the shapes. If you have only 2 hybrid orbital for the carbon, you would get 180 bond angle. If you have 3 hybrid orbital for each carbon, you would get bond angle of about 120. And if you have 4 hybrid orbital, you would get 109. The valence shell electron pair repulsion theory, it is valid. It does explain the shape of the molecule. But hybridization for carbon is much easier. I mean, we can save some time. Don't worry about the VSPR at this point, but it can explain the shape of the molecule, because we could say that VSPR stands for the valence shell electron repulsion. Same idea as bringing the orbitals together. They repel each other as much to get to the most stable position, and that would be the maximum distance, because electron, they repel each other. We could still use that electron repulsion concept for hybridization as well. So can you tell me what is a sp hybrid orbital? Can anyone tell me what does sp hybrid means? When s and one s orbital and one p orbital. Very good. One s and one p orbital. Okay. Okay, we are trying to explain formation of sp orbital. We talked about sp3, now is sp, and then we are going to use combine them all and review them. A molecule of acetylene. How many bonds this carbon forms? Or how many bonds does it have? 4 bonds. Perfect. We have 4 bonds for it. And if we start with the carbon in original form of electron configuration, it allows only with 2 bonds only. So we must take 1 electron from here and bring it to the p orbital. Now it allows us 4 bonds. If it allows us 4 bonds, if we hybrid s orbital with 3 p orbitals, it's not going to justify the shape of acetylene because shape of acetylene is linear. Now, if you have linear shape and 2 domain, that means this carbon is attached to 2 other elements. That means your hybridization was a sp hybridization because that is a 180 degree. So what does the sp means? It means the 1 s orbital and 1 p orbital is going to hybrid. So we are going to end up after hybridization. I mixed excitation, the same diagram. So if we go to the hybridization, we are going to have these 2 mix. So we are going to have these 2 orbital that is forming, and we call them sp and sp. They have 1 electron and 1 electron each. What happens to the other 2 p orbitals? They are unhybrid p orbitals because we only use 1 of the p orbitals to form the hybrid. The other 2 is going to stay the same energy level they had and is going to be perpendicular. It would be okay, I didn't get to. It would be an s orbital from 1 atom mixing with the p orbital of another. No, it's the same atom. Hybridization happens between orbitals of the same atom. So we're talking about carbon here. So s orbital from carbon and the p orbital from carbon. And these are going to be unhybrid p orbitals. So if we have an sp orbital, this is going to be carbon with the 2 orbital, and the carbon with 2 orbital is going to form a linear shape here. That's like knotting the end of 2 balloons together, maximum distance. So it's going to be, each one is going to be sp, and this is going to be sp. What happens to the py is going to stay here. This is your py. What happens to the pz? The pz is going to be this one. So you see what you did to this poor atom of carbon. First, you excite 1 electron from 2s to go to 2p. Now you have 4 single electrons. You mix only 2 of them to get the hybrid orbital, because that's the only way you can justify this 180 angle that you have here for acetylene is a 180. And these 2 p orbital is going to stay perpendicular to the center of the carbon. So what happens to the other carbon atom? What is the hybridization for this carbon atom? Can you tell me what's the hybridization for the other carbon atom? Also sp, because it's linear and it has a only 2 electron domain, so it's linear. So the other carbon of the same hybridization, so we have a carbon here, same hybridization with sp, and then you have a py that is perpendicular, and you have a pz that is perpendicular. So what type of bonding is forming when the sp orbitals overlap? Sigma or pi? What type of bonding is this? The 2 sp, this bond. What type of bond is this forming here? Is this sigma or pi? What's the only condition that the pi is going to form? Pi is going to form if you have 2 perpendicular p orbitals. These are not perpendicular, these are head-on. So this is going to be forming a sigma bond. So this is a sigma bond here. Now, what type of bonding is going to form between the, when you bring these two closer, because when the bond forms, it gets closer. So you kind of bring the p orbitals together, making the p orbitals forming like overlapping. So what type of bonding is going to between the p axis? Half a pi up, right? And then half a pi down, because this is up and down. The loops from the top and the bottom, they overlap and it forms a pi bond. What about the green color? What are the green colors? Green colors are the two of the p orbitals that they are parallel to each other because both of them are aligned with the z-axis. So the other p orbital is going to form also a pi bond. Your sp hybrid from each carbon is going to form one sigma bond between the carbon-carbon. The other sp orbital is going to form bond with the hydrogen. So you get your sp forming bond with the carbon and then with the hydrogen. So you see this is like linear shape. The pi bonds are coming from overlapping of unhybrid p orbital. You have two unhybrid p orbital for this sp hybrid carbon, and then you have two unhybrid orbital, p orbital that is on the carbon on the right side. So when you bring it together, this bond now is going to be a triple bond. So this is just showing how the triple bond is forming. You might know it, you might need to know it just for this chapter, but from now on, all you need to know is that anywhere you see a carbon, let me change the color, maybe blue is better. If you have carbon-carbon triple bond in a molecule, and you are asked, what is the hybridization for this carbon? Your answer, even if they wake up middle of the night, it should be sp hybrid. How do you know it's sp hybrid? Because only carbon with the sp hybrid can form triple bond. What is the hybridization for the other carbon? Good, did I wake you up? Okay. What is the hybridization for this carbon? Can you just tell me, is it sp or is not sp? Not sp, very good. Not sp, thank you. Okay, it's not sp. How do we know? We know is not sp because that carbon does not have triple bond. Only carbon with 2 pi bond is going to have sp hybrid. If you have a carbon with 2 pi bonds, it could be triple bond or 2 pi bond, one on each side, is going to be sp. If you have a carbon, looks this, what is the hybridization of that carbon? How is that different from this red color here? What is the hybridization for this carbon? This carbon has how many pi bonds? The top one, this one. How many pi bonds do you have? 1 pi bond on the right side, 1 pi bond on the left side. So if I only teach you this with the triple bond and on the exam I bring this question, you're not going to be able to answer that. So I show you based on number of pi bond instead of just a triple bond. Triple bond is what the book says. And then I always emphasize number of pi bonds because number of pi bonds is more crucial, because if you have a carbon with 2 pi bond, it's to be sp hybrid. A carbon with 1 pi bond, this is a double bond, but is only 1 pi bond, is going to be sp2. If your carbon has only 1 double bond is going to be sp. Now, if you have a carbon that has no shown double bond or pi bond at all, this carbon, if it doesn't show, that means there are hydrogen, that hydrogen can only form single bond. So it's 4 single bonds. And 4 single bonds is called 4 sigma bonds. So this is going to be sp3. So if you have 4 sigma bonds for carbon, the hybridization is sp3 and the bond angle is 109. If you have 3 sigma and 1 pi bond, is going to be sp2 with 120, about 120, sometimes it's 121, so it's about 120. This is about 109. If you have 2 sigma and 2 pi bonds, for carbon is going to be sp hybrid 108. You can write other notes to yourself that these are all single, bond, 1 double bond, 1 double bond only. This would be 2 double bond or 1 triple bond. So if your carbon has 2 double bonds or 1 triple bond, the hybridization is going to be sp. If it has 1 double bond only, it's going to be sp2. If it has all single bond, it's going to be sp3. Do you have any questions for me? No? Okay. At one point today, I'm going to talk about the quiz. I noticed that we have many people absent today because they looked at the I assume, I hope it's wrong, that they look at they watch the video and says, it's the same thing, I'm going to watch the video, why do I have to wake up 8 o'clock? So I'm not going to record when we are talking about quiz. So only people who actually attended the class, they get to know the type of questions that you will have on the quiz. That would be I don't know what to call that, a trick for people to attend the class. Because then they can answer me quickly right away and then we could go and ask questions. Okay, SP meant a ratio. Yes, SP means 1 s orbital and 1 p orbital. Very good. SP also means a linear structure for around that carbon. A carbon that has sp hybridization is going to be linear. The structure around it is going to be linear, and the bond angle is going to be 180. So sp means ratio. That means 1 s and 1 p orbital. But if you have 1 s, 1 p orbital, is going to give you 2 hybrid orbital, and only hybrid orbital is going to determine the shape and the angle for the central atom, and that's how we can justify the shape and the bond angle for the carbon that has sp hybrid. Very good. Very good. Okay. You're welcome. sp2, here's the shape for sp2. The blue and the green color here, that is the unhybrid p orbital. So basically, one s orbital with 3 p orbital from carbon forming, I'm sorry, one s orbital and 2 p orbital from carbon. It's forming 3 sp2 orbitals. So sp2, sp2, and sp2 orbitals, each one with 1 electron. If you have 3, as I showed you in using the markers here, the bond angle is going to be 120. The bond angle is 120 for sp2 hybrid, and the shape is trigonal planar. If you have sp2, you are going to be left with 1 unhybrid orbital. If you have two of the okay, trying to get back to the if you have 2 carbon with sp2, I was looking for empty slide so I can draw that for you, or more space so I could draw it. Let me go back to this one. So if you have a carbon with sp2 hybrid, so it's a carbon with sp2 hybrid. You have another carbon with sp2 hybrid, and if it's sp2 hybrid, it is understood that there is an unhybrid p orbital. These are sp2, 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 and there is a 1 p orbital perpendicular to the center. Then you have p orbital that is perpendicular to the center for the other one, and these are sp2, sp2, and sp2. What type of bonding would be forming if you have the 2 sp2 overlapping? The 2 sp2 overlapping is going to give you what type of bonding? The sigma bonding. Very good. A single bond, and it is a sigma bond because it's a head-on overlap. And when you bring when this sigma bond forms, the 2 carbon actually get close to each other, close enough for this 2p orbital to touch each other and overlap side by side. And when the 2p orbital overlaps side by side, a new bond forms. And what do you call that new bond that is forming from side by side overlap? It's going to be a pi bond. So we have half a pi up, I'm sorry, and half a pi down. Together, this is going to be 1 pi bond. And this is going to explain the bond angle, because sp2 is going to be 120, and it shows the shape of the molecule around this center of the carbon is going to be trigonal planar. It looks like a triangle again. And the number of the pi bonds that you have. So if you have a molecule that is molecule of ethylene, hybridization for this carbon is going to be sp2. Why is sp2? Because it has 1 double bond, or it has 3 sigma bond and 1 pi bond. In any way that you remember better, it's good with me. Okay. Okay, because, good question. Why is half a pi up, half a pi down? It doesn't matter how hard you work. It looks like the house that I said is built with the hole in the middle. If you bring 1 p orbital and another p orbital, overlapping. You get like overlap orbitals here, overlap orbitals here, and there is the empty space here. Electron cannot be in there. So electrons can spend time up here and down here. So these are the two loops. And they just say, don't think that this is two bonds. It's one pi bond. Because when you bring the p orbital from the right side with the p orbital from the left side together, you are going to get two pi bonds. You are going to get two molecular bonds, but one of them is going to be pi. The other one would be pi with the asterisk. This is bonding, and this is the anti-bonding. So for you not to make a mistake that this is like, do you see two clouds up and down? It's two bonds. They say, no, no, no. This is half, and this one is half. And together is one pi bond. I hope I answered the question. Right? Good? Perfect. You're welcome. NH3. Now, when you are counting or determining hybridization, you count electron domain. To count electron domain, you are going to count single bond as one, electron domain, or electron group, just like VSPR, electron domain or electron group. Double bond counts as one electron group, and triple bond counts as one electron group. And if you have pair of unshared electrons, that's pair of electron. Each electron pair is going to count as one electron group. So please make sure to write these somewhere, because I'm going to use the same page for the next table. If you have 4 electron groups, for 4 electron groups, then the hybridization is going to be sp3. For 3 electron groups, hybridization is going to be sp2. And where do you find the electron groups? Is going to be around the central atom. So you're counting how many electron group is attached to carbon. If you have 2 electron groups, the hybridization is going to be sp. Also write this down somewhere, because now I'm going to use examples to determine hybridization. Examples: N, CH3, CH3, CH3. What is the hybridization for nitrogen here? Instead of hybridization, let's take one step at a time, and we count the, very good, and we count the electron groups. How many electron groups do we have for nitrogen? We have 1 electron group here, because 1 sigma, another electron group, and 4 electron group. Very good. We have 4 electron groups, and we said if the central atom has 4 electron group, it's going to be sp3 hybrid. It's going to be sp3. Now, for ammonia, when they measure the bond angle, this bond angle, it's not 109 and is the 107. And then after they solved all the problems for the bond angle, because the valence bond theory could not explain it, hybridization could explain, then they come and they look at this. Okay, so how come it's 107 and is not 109? Then they have to justify this. It says, well, if you have methane with 4 electron groups, the bonding electrons that is shared between carbon and each hydrogen, they are going to not like each other, they are going to repel each other. So this is going to be repelled, this is going to be all repelling each other, and it looks like that you have 4 balloons that unite the ends together. They take the maximum space from each other, and they give you perfect tetrahedral. But when it comes to ammonia, for ammonia, you have the electron repulsion between the bonding or shared electrons, and you have electron repulsion for the non-bonding. The electron repulsion between the non-bonding or pair of unshared electron preferably, it's going to be stronger. So this force is stronger. There is a force here, there is a force here, but this force is stronger. And that stronger force is going to reduce the bond angle for this hydrogen, nitrogen, hydrogen from 109 to 107. So this is just explanation why bond angle for ammonia is 107, even though the hybridization based on these shortcuts we found out to be sp3. So we explain based on electron repulsion or strong electron repulsion for pair of unshared electron that we have on nitrogen. Another example, water molecule. Can you tell me what is the hybridization for oxygen? How many electron groups do we have, and what is the hybridization? 4 electron groups, sp3, very good. Everyone agrees with that? sp3. What is expected bond angle? Expected 109, about 109 or exactly 109.5, that's perfect. Now, what is the actual bond angle? 105. How would you justify this? To justify the bond angle for water, you cannot say 180 because water doesn't look like this. Based on hybridization of oxygen, this is going to be tetrahedral, and the bond angle is going to be 109, about 109. But how do you justify this? This is, you have now 2 pairs of unshared electron. So that repulsion is even stronger when you have 2 pairs, and since it's stronger for the 2 pairs, it's going to reduce from 109 to 105. Okay, good question. How do they determine the actual value? There is a nucleus here, there is a nucleus here, and there is a nucleus here. If you take X-ray of your hand, it only shows the bones, right? If you take X-ray of the molecule, it shows the nucleuses, because in the nucleus you have the mass of the atom is in the nucleus. Everything else is like basically empty space. Electrons don't have much of a mass, and it doesn't show in the X-ray that is used for chemistry, for determining structure. So they find this, they connect this dot, they measure this, and it becomes 105. So they actually use X-ray to determine the bond angle. They also can use this to X-ray to find the bond length also. Certain bond angle is just the 3 that you need to know. The sp3 is going to be 109, sp is going to be 180, and sp2 is going to be 120. Because you're dealing only with carbon, you don't have a lot to worry about. But these 3, yes, you need to know. That is the question. And that's the actual is just if the number will be given to you and you are asked to, you could be asked to justify it, but you don't have to remember the exact number. They might ask, is it going to be 109? For example, for this is going to be 109 or not? Would it be less than 109, more than 109? If it's multiple choice question, then you could consider this a strong repulsion and would be slightly less than 109. It's not going to go to 90 degrees. It's not going to go, to different number. And this is not going to be 120 because nitrogen has 3 bonds. And if you don't count the pair of electron as electron domain, you might say, or 3 bonds is going to be 120 also. So for first, you determine the sp3, and in order to determine the sp3, you must have the Lewis structure, because Lewis structure, it shows the pair of unshared electron on the central atom. You don't worry about the pair of unshared electron on other domain atom, but for central atom, you need to have the pairs of unshared electron, and you count it as electron domain. Okay, question. Lone pairs always have a stronger repulsion than single, double, and triple bond. Yes, exactly. You're welcome. Okay. Rotation around carbon-carbon double bond versus rotation around carbon-carbon single bond. If you have a carbon-carbon single bond, you can rotate the molecule, and rotation, it doesn't take much of an energy. So if you have a single bond, let's say you have a single bond, you see my hands, okay, you have a single bond here, you have to you can rotate this. Rotation around single bond is easy. I've used this example and they said that it does help. Now if you have a double bond, let's say I have a double bond here. If I have a double bond, you can try this with your own hands to put the two together, like align it properly and make the double bond, and try to bring your thumb up with the right hand. It's very hard, right? It is very hard. So you cannot rotate around carbon-carbon double bond, but you can rotate very easily around carbon-carbon single bond. You can rotate it. Now, in order to rotate, what you need to do, you need to break one of these bonds, rotate, and form a new bond. So rotation is possible, but you have to break a bond, form a new bond. You break this bond, you rotate, and then form a new bond. And in this case, it's a chemical reaction, actually. Breaking bond, breaking old bond, forming new bond is a chemical reaction. So if you have a carbon-carbon double bond for your molecule, then depends on the structure. So let's say you have a CH3's up in both cases, hydrogen's down, and another molecule, one CH3 up, one CH3 down, one hydrogen down, hydrogen up. Compound A and compound B are not the same. And these two, with respect to each other, they are known as isomers, and these are geometrical isomers because the molecules are, connectivity is the same. The only difference is that orientation is, space is different. You have two CH3s on the same side, CH3, one CH3 on each side. So if you had this before in Gen Chem, this is going to be trans, and this is going to be cis isomer. Cis isomer, trans isomers. We will get to this one more time, but right now my emphasis was on the rotation around carbon-carbon single bond, which is free, but rotation around carbon-carbon double bond is not free of energy, and for that you have to break the pi bond, you have to rotate, and then the pi bond has to form again, which is going to end up with a new compound. Hybridization and the geometry. Sigma bond and lone pair can occupy one hybrid orbital. If it's a double bond, it would occupy one hybrid orbital. And then lone pair needs to be calculated. So basically the tables that you had already. Let me see what we have here. Each 2 carbon hydrogen form sp. Okay, so it's just showing that you have sp hybrid here, sp hybrid, and sp hybrid. And if it's a sp hybrid, your carbon most likely is going to have a triple bond, and the double bond, the pi bond, is coming from overlap of the parallel p orbitals. So I already explained about those. Rotation, it's free. Rotation around carbon-carbon double bond is not free of energy, so you get the cis versus trans. Cis, the same groups are on the same side, and trans, the same groups are on the opposite side. Based on these two structures, can anyone tell me, I don't expect you to know it, but I just want to see, you can imagine which one is more stable? The cis is more stable, or trans is more stable? Trans is more stable. Very good. Trans, because of the remember for the VSPR, I said is electron repulsion or valence shell electron repulsion. Electrons don't like each other. We know that from general chemistry. What we know from organic chemistry, groups they don't like to be hindered at all. They want to have maximum space to each other, to themselves. So the further apart they are from each other is going to be more stable. For trans, because the CH3 groups are further apart from each other, is going to be more stable than the cis configuration or the cis isomer, because these two are close to one another. Double bonds cannot rotate, but you have to break a bond and rotate, form a new bond. Okay. Molecules with the same, let's see if I can turn on the other computers. Molecules with the same molecular formula, different structural formula, they are known as isomers. We have geometrical isomers, just like the ones that I just showed you for cis and trans. We do have constitutional isomers, and for constitutional isomers or structural isomers, the isomers, these isomers are the ones that, you can go. These isomers are the molecules that they have different connectivity. Like this for N-pentane versus isopentane versus new pentane, they all have 5 carbon and 12 hydrogens. 5 carbon, 12 hydrogens. But when it comes to connectivity, for N-pentane or normal pentane, you have everything aligned and no carbon is attached to more than 2 other carbons. For isopentane, you have a carbon that is attached to 3 carbon. For new pentane, you have carbon that is attached to 4 other carbons. So these are different connectivity. So if it shows different connectivity, but the molecular formula still is a C5H12, these are isomers with respect to each other. Stereoisomers or geometrical isomers. If you have a carbon-carbon bond, you could have cis-trans isomers with the condition that the two groups that are attached to the same carbon, they are different. Because if you had a hydrogen here and you rotate it, it would be the same molecule. The resonance can't be changed in structure, only the electron bonds. Very good. That is resonance structures for chapter 1, and this is isomers for chapter 2. Very good. Then that's resonance, actually recognizing if the two structures are resonance of one another, is going to be a question in your quiz and in your exam, because it's just moving of the pair of electrons, or moving plus charge, moving pi bonds by one, and then moving charge by 2, or just moving pi bond and moving electrons and moving plus charge. But you cannot move around the molecule or rotate the molecule for resonance. For isomers, you can change the connectivity for structural isomers. For geometrical isomer or stereoisomers, only orientation in the space is going to be different. So for cis, you have two CH2s and same group, same side, and for trans, is going to be in the opposite side because there is no free rotation. Very good. Okay. Polarity of the molecule, polarity of the bonds. We talked about the polarity slightly, but I just want to tell you about why, because some of you have lab soon, why polarity is important for us. In order to determine polarity of the molecule, you must draw the Lewis structure and then see if the groups attached to central atom, they are going to be the same or they are going to be different. If you have pair of unshared electrons, it's going to be polar because there is not same as the bonds. Now, how is going to help us if we know a molecule is polar? General rule for solubility is that like dissolves in like, polar compounds dissolves in polar solvent, non-polar dissolves in non-polar. So if we know the compound is polar, we can expect that compound to dissolve in water or in polar solvent. If we know the compound is non-polar, then we can say that it's going to not dissolve in water. Compounds that they are polar, they have dipole-dipole interaction, which is stronger than the van der Waals or London dispersion intermolecular forces. So molecules that are polar is going to also have high boiling point and high melting point. Okay, as I promised, I'm going to stop here. I will answer a few questions, and then I'm just going to say type of questions that you would expect in the quiz, because someone asked for review. No, I'm not going to put a review for quiz. It's a whole chapter. And when you take a quiz, it's actually helping you to see the type of questions that you might see on the exam. And also is not going to be very challenging at all. Your challenging problems, the most challenging ones are the co-op. Then you have the OR app. Those are easy. The only thing you have to do is to open the book and PowerPoint and go back to the chapter, go back to the PowerPoint and find the answer, and make sure that you start from question 1, because going from question 1 to question 20 is going to build up skills on each other. So if you don't do question 5 and you jump to question 10, it's going to be challenging. But if you do question 1, 2, and then just consecutively, it's going to make it much easier for you. Okay, do you have any questions for me? Questions for me? No questions? We stop to record.